The universe is mostly empty space, a silent ocean of darkness we call the cosmic void. Yet this apparent emptiness is an illusion, concealing puzzles so profound they challenge our very understanding of reality. We are about to embark on a journey through 25 of the cosmos's greatest enigmas. You will discover the invisible substance sculpting galaxies, the phantom force tearing reality apart, and signals from the depths that might just be messages from another world. What cosmic secret would rewrite our story entirely if we uncovered it today? Our universe is held together by a ghost. We watch galaxies spin, their outer stars whirling at speeds that should tear them apart and fling them into the black. Yet they remain bound, orbiting as if gripped by an invisible hand. This unseen hand belongs to dark matter. We cannot see it, touch it, or detect it with any instrument we have ever built. It neither emits nor absorbs light. Its presence is revealed solely through the relentless pull of its gravity. Without this mysterious substance, galaxies would simply fly apart. Think of a merry-go-round spinning so fast that the children clinging to the edges are hurled away. Now picture that same ride with the children held safely in place by an unseen force. That is the role dark matter plays on a cosmic scale, a cosmic glue preventing the universe from unraveling. Scientists call the search for its true identity one of the greatest detective stories in physics. The prime suspects have names straight from science fiction. WIMP, or weakly interacting massive particles, are hypothetical heavy particles that barely interact with normal matter, passing through our planet, our homes, and even our bodies by the billions every second without a trace. Then there are actions, particles so incredibly light and ghostly they were theorized to solve a different puzzle entirely in particle physics. These are just two of the leading candidates in a hunt that has spanned decades, a hunt that has so far come up empty. We have built detectors deep underground, shielded from cosmic rays, waiting for the faintest whisper of a collision with a dark matter particle. We have pointed telescopes at the heavens, searching for the indirect signals of dark matter particles annihilating each other. And yet the ghost remains at large. This is not a minor component of reality. This invisible scaffolding makes up roughly 27% of everything in the cosmos. All the stars, planets, nebulae, and galaxies we can see and dream of visiting account for less than 5%. The rest is dark matter and its even more mysterious counterpart, dark energy. We are living in a universe dominated by forces we do not understand, looking out at a cosmic map where the most important features are drawn in invisible ink. What is this substance that holds the fate of galaxies in its grasp, yet remains forever hidden from our view? The answer is out there, waiting in the dark. If dark matter is the ghostly glue holding the cosmos together, then dark energy is its shadowy opposite, a force of cosmic repulsion. While one pulls the universe inward, the other is pushing it apart at an ever-increasing rate. This discovery in the late 1990s sent shockwaves through the scientific community. Two independent teams were observing distant stellar explosions, known as Type 1, a supernova. These events are crucial because they act as standard candles, their known intrinsic brightness allowing astronomers to gauge cosmic distances with incredible precision. The researchers expected to see the expansion of the universe, confirmed decades earlier by Edwin Hubble, slowing down over time due to the collective gravity of all matter. Instead, they found the opposite. The most far-flung supernova were significantly dimmer than their predicted brightness, meaning they were much farther away than anyone had calculated. The universe was not just expanding, it was accelerating. This was not a gentle nudge, but a powerful and relentless push. The force responsible was given a name, dark energy. It behaves as a kind of anti-gravity, a repulsive effect woven into the very fabric of empty space. Imagine blowing up a balloon with tiny dots on its surface. Now imagine the rubber of the balloon itself starting to stretch faster and faster, forcing the dots to rush away from each other at an accelerating pace. The dots are not moving through the balloon, the space between them is actively growing. That is the effect of dark energy on our cosmos. The implications are staggering. This mysterious component is not a minor player. It is the single greatest constituent of the universe, making up about 68% of everything that exists. What could it possibly be? The leading theory suggests it is an intrinsic property of space itself. According to this idea, even a perfect vacuum, the truest empty space, possesses a fundamental energy that causes it to push outward. This concept, a cosmological constant, was first proposed by Albert Einstein and later discarded as his greatest blunder. It seems he may have been right for the wrong reason. Another possibility is that dark energy is a dynamic field, a new kind of energy that permeates the cosmos, its strength changing over time. Could this force eventually become so powerful that it tears apart galaxies, stars, and even the very atoms that make us? The fate of the entire cosmos, from the largest galaxy clusters to the smallest particles, hinges on the true identity of this enigmatic energy. We are left watching the stars recede, propelled by a mystery that defines our ultimate destiny. Our galaxy is not merely drifting through the cosmos, it is being pulled. The Milky Way, along with our entire local group of galaxies, is racing toward an unseen destination at a staggering 14 million miles per hour. This monumental force has a name, the Great Attractor. It is a gravitational anomaly of almost unimaginable scale, a focal point in the void that commands the motion of thousands of galaxies. We are caught in a cosmic current flowing toward a mystery. The greatest frustration for astronomers is that we cannot see what is pulling us. The Great Attractor lies in a region of the sky known as the zone of avoidance. This is not a place of true emptiness, but rather a thick shroud of cosmic dust, gas, and countless stars that constitute the plane of our own Milky Way galaxy. It is like trying to see a distant city from the heart of a dense, foggy forest. The very trees of our home galaxy block the view. For decades, this zone was a blind spot in our maps of the universe. So what could possibly possess enough mass to exert such a powerful gravitational tug? Early theories suggested it was a massive concentration of galaxies, an immense supercluster that we simply could not see. As observing techniques improved, allowing us to peer through the galactic fog with infrared and radio telescopes, we began to get glimpses. We now know there is a colossal gathering of galaxies in that direction, a structure known as the Norma cluster. But the puzzle deepened. The sheer number of galaxies we have found does not seem to fully account for the immense pull we feel. There must be more mass there, much more, hidden behind the first layer of the mystery. This leads to the unsettling possibility that the Great Attractor itself is merely a waypoint, a signpost on a much longer journey. Some evidence suggests our local motion is part of an even vaster flow, pulling us toward an incomprehensibly large structure far beyond, known as the Shapley Attractor. If true, then the Great Attractor is just the first ripple of a distant waterfall, a local manifestation of a gravitational pull from the most massive concentration of matter in our observable universe. Is it a known structure we simply cannot see in its entirety, or is it something more exotic, a concentration of dark matter so dense it warps the fabric of our local cosmos? The answer remains hidden, a colossal shadow in the zone of avoidance, silently drawing us in. Our relentless journey toward the Great Attractor raises a profound and unsettling question. If the cosmos is so vast, filled with hundreds of billions of galaxies, each home to hundreds of billions of stars, then where is everybody? This is the heart of the Fermi paradox, a cosmic contradiction that grows more puzzling with every new exoplanet we discover. The numbers alone suggest a universe teeming with life. There are more potential worlds in the observable universe than there are grains of sand on every beach on Earth. With such staggering odds, the silence from the cosmos is deafening. Why have we not found any evidence, not a single artifact, signal, or engineering project that points to intelligence beyond our own? One potential answer is as terrifying as it is simple: the Great Filter hypothesis. This idea suggests that the evolution of life from its origins to a spacefaring civilization requires passing through a series of nearly impossible challenges. This filter could be a cataclysmic event, a natural barrier so severe that it prevents almost all life from advancing beyond a certain point. Perhaps the filter lies in our past, something we have already survived, like the miraculous jump from simple prokaryotic cells to complex eukaryotic life. If so, we might be the first and only species to have made it this far. The more chilling possibility is that the Great Filter awaits us in our future. It could be that all technological civilizations inevitably discover something, a particle physics experiment that unwittingly destroys a star, or an artificial intelligence that turns on its creators, a discovery that becomes their doom. Another possibility redefines the nature of intelligence itself. What if advanced civilizations are not just far away, but are fundamentally unrecognizable to us? Their technology, their methods of communication, their very existence might be so advanced that it is indistinguishable from the laws of physics. They might not use radio waves, but something we cannot yet conceive of, like manipulating space-time itself. To an ant colony at the base of a radio tower, the structure is just part of the landscape, not a deliberate construction. Could we be the ants surrounded by cosmic engineering we are simply too primitive to see? Then there is the loneliest answer of all, that we are truly alone. In this immense, dark ocean of a universe, our pale blue dot might be the only island of consciousness, a solitary flicker of thought in an endless, silent night. The sheer scale of the cosmos would then be the universe's greatest irony, a stage built for an audience of one. Each of these possibilities carries a profound weight. Are we the lucky survivors, the doomed pioneers, or the solitary children of a silent cosmos? The answer to the Fermi paradox will tell us not just who else is out there, but what our own ultimate fate may be. That profound cosmic silence was broken, if only for a moment, on a summer night in 1977. A volunteer astronomer named Jerry Amon was meticulously scanning data printouts from Ohio State University's Big Ear radio telescope. His eyes locked onto a string of characters so extraordinary he circled them in red pen and wrote one word in the margin: "Wow." The sequence, 6 letters and numbers, represented a powerful, narrowband radio signal that lasted for 72 seconds. It came from the direction of the constellation Sagittarius, and it was a perfect match for what scientists had predicted an artificial, interstellar signal would look like. It was not random noise, not a human broadcast, and not a signal from a passing satellite. It was a scream in the silence, a burst of pure, ordered energy that seemed to have no natural explanation. The excitement was electric. Had we finally received a message? The Big Ear telescope, however, was a fixed dish that relied on the Earth's rotation to scan the sky. By the time anyone could point another instrument at that exact spot, the signal was gone. Decades of follow-up observations using far more sensitive equipment have found nothing. Not a whisper, not an echo. The WOW signal appeared, declared its presence with shocking clarity, and then vanished forever into the static. So what was it? The debate continues to this day, a mystery fueled by that single, perfect data point. Some astronomers propose a natural, though incredibly rare, celestial event. Perhaps it was a comet emitting a powerful burst of hydrogen as it passed through a cloud of interstellar gas. The problem is that no known comet was in that region of space at that exact time. Others suggest it was a signal reflected off a piece of space debris, a fleeting echo of our own technology bouncing back at us from the void. Yet the specific frequency and intensity make even that explanation difficult to accept. Then there is the possibility that it was exactly what it seemed, a deliberate broadcast, a lighthouse beam from a distant civilization, sweeping past our solar system for just over a minute, a hello that we heard but could not answer. Was it a message meant for someone else and we simply happened to be in the way? Or was it a test signal from an alien probe momentarily activated within our range? The truth is, we may never know. The wow signal remains the most tantalizing, frustrating, and enduring candidate for a message from the stars in the entire history of the search for extraterrestrial intelligence. It is a ghost in the machine of science, a one-night stand with the cosmos that continues to haunt our imagination. What if we had been listening just a little bit longer, or had been just a little bit quicker to respond? That single, silent question mark hanging in the dark is a reminder of how lonely the universe can feel after a brief, unconfirmed hello. The profound silence that followed the wow signal taught us a difficult lesson about cosmic communication. Yet decades later, the universe began to speak again, not with a single mysterious word, but with a volley of brilliant, fleeting shouts. Astronomers call them fast radio bursts. These are not gentle signals, they are titanic explosions of radio wave energy, each one releasing more power in a single millisecond than our Sun emits in 80 years. The first one was discovered in 2007, buried in archival data from a radio telescope in Australia. It was so brief and so bright that for years, many in the scientific community dismissed it as a one-off glitch, an instrument error, or perhaps a local terrestrial interference. But then we found another and another. These cosmic firecrackers were real, and they were coming from the deepest reaches of intergalactic space. The central challenge with fast radio bursts is their breathtaking brevity. They flash into existence and vanish before you can even blink, leaving behind only a ghostly fingerprint in a telescope's data stream. For years, they were like a camera flash going off in a dark, crowded room. You knew it happened, but you had no idea who held the camera. Pinpointing their source seemed nearly impossible. The breakthrough came with painstaking work and newer, faster telescopes. We began to catch them in the act, tracing a handful of these bursts back to their home galaxies, which lie millions, even billions of light years away. This confirmed their immense power and their extragalactic origin. They were not local phenomena, they were messages from the cosmic depths. So what natural engine could possibly create such a violent, short-lived flash? The list of suspects is as fascinating as the mystery itself. One of the leading candidates is the cataclysmic merger of two ultra-dense neutron stars. As these stellar corpses spiral into each other, they could unleash a final, concentrated blast of radiation just before collapsing into a black hole. Another compelling theory points to magnetars, a special class of neutron stars with magnetic fields so intense they are literally unimaginable. A starquake on the surface of a magnetar, a crack in its crust under unimaginable strain, could release a shiver of energy so powerful it ripples across the universe as a fast radio burst. We have even detected one such burst from a known magnetar within our own Milky Way galaxy, lending significant weight to this idea. Yet for all the compelling natural explanations, a small, tantalizing possibility remains. The bursts are so energetic, so brief, and some even repeat in seemingly random patterns. Could we be witnessing something else entirely? A small group of scientists has speculated cautiously about the possibility of artificial origins. What if these are not natural explosions, but the result of advanced technology? Perhaps a civilization capable of interstellar travel uses incredibly powerful radio bursts to push light sails across the galaxy. Each burst would be a pulse from a cosmic engine, a beacon firing for a millisecond to accelerate a probe to relativistic speeds. The idea seems like science fiction, and it likely is, but the sheer power and strangeness of these events force us to consider every possibility. Fast radio bursts are a reminder that the cosmos is not a quiet, static place. It is a dynamic and often violent arena where energies beyond our comprehension are routinely unleashed. Each new flash captured by our telescopes is another piece of a puzzle, a piece that could lead us to a new class of stellar object, a new law of physics, or perhaps to something even more extraordinary waiting in the dark. Even the most precisely charted journeys can hold hidden surprises. The twin probes Pioneer 10 and Pioneer 11 were humanity's first emissaries to the outer solar system, their trajectories calculated with exquisite care. Yet as they ventured beyond the orbit of Pluto, a faint but persistent whisper of a problem emerged. They were slowing down, not by much, just a tiny, almost imperceptible amount, equivalent to a 10 billionth of the gravity we feel on Earth. But in the pristine silence of interplanetary space, this minuscule deceleration was a loud anomaly. For years, this pioneer anomaly baffled physicists. Was it a sign of some unknown drag from tenuous interplanetary dust? Could it be a subtle flaw in our understanding of gravity itself? A hint that Einstein's theory of general relativity needed a slight tweak at the solar system's edge. The search for an answer became a decades-long forensic investigation. Scientists had to become cosmic detectives, sifting through decades of old engineering data and blueprints. The culprit, it turned out, was not a new law of physics, but something far more mundane and yet incredibly difficult to quantify. The spacecraft were powered by radioactive thermoelectric generators, and these units produced heat. That heat, radiating from the spacecraft's electrical systems and plumbing, acted like a tiny, gentle photon thruster. Each time a thermal photon was emitted in a particular direction, it gave the spacecraft a minuscule push in the opposite direction. It was the cumulative effect of billions upon billions of these tiny photon pushes, all acting preferentially against the direction of travel, that created the faint but measurable deceleration. The mystery was largely solved, a triumph of meticulous engineering analysis over exotic physics. Yet, for some, a ghost of a question remains. Does the refined thermal model account for every last fraction of the observed slowdown? Or is there still a whisper of something else, some other tiny force acting upon our furthest robotic travelers, a final secret the pioneers carry with them into the endless night? Beyond the orbit of Neptune lies a frozen frontier, a vast disk of icy debris known as the Kuiper Belt. This is the solar system's attic, a graveyard of primordial leftovers from our planetary formation. Yet this distant realm holds a sharp and puzzling boundary, a place where the cosmic clutter simply stops. Astronomers call it the Kuiper Cliff. Based on our best models of how the solar system was born, this region should be teeming with thousands of small, icy worlds for billions of miles. Instead, the population of objects drops off a precipice, plummeting to almost nothing at a distance of about 50 astronomical units from the Sun, which is 50 times farther than Earth is from the Sun. It is as if you are walking through a forest that abruptly ends at a straight, clean edge with nothing but empty fields beyond. This sudden emptiness makes no sense. The original protoplanetary disk, the swirling cloud of gas and dust that gave birth to all the planets, should have extended much farther out, leaving behind a gentle gradient of objects that slowly thins into the void. The Kuiper Cliff is not gentle, it is a stark and dramatic wall. So what could have carved this edge into our solar system? One compelling theory points to the gravitational hand of an unseen architect, a massive object whose distant orbit shepherds the Kuiper Belt. This is the hypothetical planet 9, a world perhaps 10 times the mass of Earth, lurking hundreds of times farther from the Sun than we are. Its immense gravity, the theory suggests, could have sculpted the orbits of the most distant Kuiper Belt objects, clearing out a vast swath of space and creating that sharp cliff. We have not yet seen this planet, but the peculiar, clustered orbits of several extreme trans-Neptunian objects hint strongly at its presence, like seeing the wake of a ship before you spot the vessel itself. Another possibility is even more dramatic, a ghost from the solar system's violent infancy. What if our sun was not born alone, but as part of a dense stellar nursery surrounded by thousands of other sibling stars? In this chaotic environment, a passing star could have ventured dangerously close to our young solar system. The gravitational pull from this stellar intruder would have been like a cosmic rake, stripping away the outermost material of the Kuiper belt and stealing it into interstellar space, leaving behind the truncated disk we see today. This would mean the Kuiper cliff is not a natural feature of our system, but a scar from a long-forgotten close encounter. The cliff forces us to confront the limits of our knowledge. Is our solar system still hiding a giant planet in its dark outer reaches, or are we seeing the fossilized imprint of a stellar flyby from billions of years ago? Each possibility reshapes the story of our cosmic home, suggesting that the history written in these icy bodies is far more eventful than we ever imagined. The quiet order of our solar system was suddenly broken by a visitor from the stars. In October 2017, a telescope in Hawaii detected a faint point of light moving at incredible speed. It was not orbiting our sun, it was just passing through. This was Oumuamua, the first object ever confirmed to have arrived from interstellar space, a cosmic wanderer from a distant, unknown star system. Its very existence was historic, but its bizarre properties turned a moment of discovery into a lasting enigma. First, there was its strange shape. Observations suggested it was not a roundish lump like most asteroids or comets. Instead, it appeared to be highly elongated, perhaps 10 times as long as it was wide, tumbling end over end through the solar system. Astronomers had never seen a natural object with such extreme proportions, a shape more akin to a pancake or a cigar than a space rock. Then came the truly confounding behavior. As Oumuamua slingshotted around the sun and headed back out into the void, something unexpected happened. Its trajectory began to deviate slightly from the path dictated by gravity alone. It was speeding up as if pushed by an unseen force. For a comet, this is a common occurrence, the result of outgassing. When a comet's icy surface is heated by the sun, it vents gas and dust, which acts like a natural rocket engine, giving it a small kick. The problem was, Oumuamua showed no visible signs of outgassing, no surrounding cloud of gas, no dusty tail. It was a rock seemingly behaving like a comet, but without any of the comet's telltale features. This non-gravitational acceleration sent scientists scrambling for an explanation. One leading theory suggests it was, in fact, a very peculiar comet. Perhaps it was an ancient object baked by cosmic radiation over millions of years, which had lost most of its more volatile ices. When it approached our sun, the heat may have released trapped hydrogen gas from deep within its water ice. This hydrogen outgassing would be invisible to our telescopes, but could provide just enough thrust to explain the acceleration. Another idea posits that it was a loose, porous aggregate of dust, more of a fractal cloud than a solid body, whose movement was affected by radiation pressure from the sun itself. Yet the most captivating and highly speculative hypothesis came from Harvard astronomer Avi Loeb. He proposed that Oumuamua's unusual acceleration and its bizarre shape could be explained if it was not a natural object at all, but a piece of advanced alien technology, specifically a light sail. A light sail is a proposed form of spacecraft propulsion that uses the gentle pressure of sunlight or powerful lasers to push a large, thin, reflective sheet through space. A discarded light sail tumbling through the cosmos would fit the profile of a very thin, oddly shaped object that accelerated without any visible outgassing. The scientific community remains deeply divided. Most astronomers lean toward a natural origin, believing it is a new type of planetary building block from another star system, one whose properties we are simply not used to seeing. They argue that invoking an extraterrestrial explanation is a last resort, only to be considered after all natural possibilities are exhausted. But the frustrating truth is that Oumuamua is now gone, far beyond the reach of our telescopes, receding into the darkness from whence it came. It left behind a trail of questions and a fierce debate about what exactly passed through our celestial neighborhood. Was it a hydrogen iceberg, a cosmic dust bunny, or a relic from a civilization far older than our own? We may never know for sure, but its brief visit taught us one profound lesson. The galaxy is likely filled with such travelers, and the next one might just hold the answer. That silent echo from the dawn of time holds a secret it was never supposed to have. The cosmic microwave background radiation is the oldest light in the universe, a fossilized glow from when the cosmos was just a hot, dense soup of particles, finally cool enough for light to travel freely. This afterglow should be the most uniform thing we can observe, a nearly perfect tapestry of minute temperature variations that confirm the universe is on the largest scales the same in every direction. This is the cosmological principle, a foundational pillar of modern science. Yet when scientists created the most detailed map of this background, they noticed something unsettling, a strange alignment, a preferred axis that runs through the cosmos like a ghostly spine. They gave this startling feature a dramatic name, the axis of evil. The name itself reflects how deeply this finding disturbs our understanding. It is not a structure made of galaxies or dark matter, but an alignment in the very fabric of the universe's first light. The hot and cold spots in the cosmic microwave background are not scattered randomly as predicted. Instead, they appear to be correlated along this vast, invisible line, suggesting the infant universe may have had a distinct orientation, a preferred direction that should not exist. It is as if you walked into a room that was perfectly round and found all the furniture subtly angled toward one specific wall. The implications are profound. If the universe truly has a preferred axis, it would force us to rewrite the textbooks. The cosmological principle would be broken, meaning our universe is not isotropic, not the same in all directions after all. This would demote our place in the cosmos from a universal average to a special location within a grand, lopsided structure. So is this axis real evidence of new physics or just a cosmic mirage? Skeptics argue it could be a statistical fluke. When you analyze a massive, complex dataset, you are bound to find some patterns that look significant purely by chance. It could also be an artifact of our own observation, a contamination from within our own solar system or even our galaxy. The light from the cosmic microwave background has traveled for over 13 billion years to reach us, and on its long journey, it must pass through the dust and magnetic fields of the Milky Way, which could potentially imprint a false signal, a smear across the pristine data. Yet, even after astronomers have worked meticulously to subtract these potential foreground effects, the strange alignment persists. It refuses to go away. This has led to more exotic explanations that venture into the realm of speculative physics. Could the axis of evil be a bruise from a collision with another universe in the vast multiverse, a remnant of a primordial trauma that set our cosmos spinning on a preferred axis from the very first instant? Or does it hint that the fundamental laws of physics are not constant throughout the cosmos, but vary depending on which direction you look, a concept that would turn all of particle physics on its head? The axis of evil remains one of the most controversial and unresolved puzzles in cosmology. It is a challenge thrown down by the universe itself, a whisper from the beginning of time that suggests our most cherished assumptions about cosmic order might be profoundly wrong. Whether it is a flaw in our maps or a crack in our principles, this mysterious alignment forces us to question if we are seeing the universe as it truly is, or merely through a distorted lens of our own making. Even the most voracious cosmic monsters might not be able to erase the past. When any piece of matter crosses the boundary of a black hole, the point of no return known as the event horizon, it appears to be lost forever to the outside universe. But according to the bedrock principles of quantum mechanics, information can never truly be destroyed. Every particle carries with it a specific set of information, a kind of quantum fingerprint that details its properties, its history, and its relationships to every other particle. This information is supposed to be permanent, etched into the fabric of reality itself. The black hole information paradox asks a devastatingly simple question. What happens to that information when matter is irretrievably consumed by a black hole? If the information is truly lost, then our entire understanding of quantum physics is fundamentally wrong. If it is preserved, then where does it go, and how does it escape the black hole's immense gravitational grip? This is not a minor technicality. It is a direct conflict between the two most successful theories of the 20th century, general relativity and quantum mechanics, and only one can be correct. For decades, Stephen Hawking presented the most dramatic answer. He believed the information was indeed lost. He argued that black holes are not completely black. They slowly evaporate over astronomical timescales by emitting a faint glow of particles, now known as Hawking radiation. This radiation, however, is purely thermal. It is random noise that carries no specific information about what fell in. In this scenario, when the black hole finally evaporates completely, all the information about the stars, planets, or astronauts it consumed would be erased from the universe forever. This idea was so troubling that it led to a famous bet between Hawking and other physicists who insisted information must be conserved. Hawking eventually conceded the bet, admitting he was likely wrong, but the question of how the information escapes remained wide open. One of the most mind-bending solutions is the holographic principle. This theory suggests that all the information about everything that falls into a three-dimensional black hole is not lost inside, but is instead perfectly preserved, encoded on a two-dimensional surface, the event horizon. Imagine spilling a bottle of ink onto a sheet of paper. The ink soaks in and seems to disappear into the paper's fibers. But if you had a powerful enough microscope, you could analyze the precise pattern of the stain and reconstruct exactly what was written on the page. The event horizon acts like that sheet of paper, recording a perfect, if incredibly complex, hologram of everything that crosses it. The three-dimensional reality we perceive inside the black hole is just a projection of that two-dimensional information stored on its surface. In this view, when Hawking radiation is emitted, it is not random. It is subtly imprinted with the information from that surface hologram, slowly leaking the data back out into the universe over eons. This principle suggests a staggering idea that our entire three-dimensional universe might itself be a holographic projection of information stored on a distant two-dimensional boundary. Are we, and everything we see, just a complex cosmic code written on the surface of the void? The black hole information paradox forces us to confront the very nature of reality, questioning whether the world we experience is the whole story or merely a magnificent shadow play. Some of the most violent deaths in the cosmos leave behind a lingering scream of light. When a star wanders too close to a supermassive black hole, it does not simply vanish. It is torn to shreds by an unimaginable gravitational force, a cataclysmic event known as a tidal disruption. The black hole's pull on the side of the star nearest to it is so much stronger than the pull on the far side that the star is literally stretched thin, a process called spaghettification. It is ripped apart into a long, thin stream of superheated gas, a stellar corpse that then wraps around the black hole in a frenzied, swirling whirlpool known as an accretion disk. This disk glows with a ferocious intensity, a beacon of destruction that can outshine an entire galaxy for months. These events should follow a predictable script, a bright flash that steadily fades as the stellar material is consumed. Yet the universe loves to break its own rules. Astronomers have witnessed tidal disruption events that defy all expectations, shining with a ferocious energy that our models cannot easily explain. Some of these cataclysms produce staggering amounts of ultraviolet and X-ray radiation, far more than the simple friction of the accretion disk should create. Others unleash powerful, narrow beams of plasma, known as relativistic jets, that shoot out from the black hole's poles at nearly the speed of light. Why do some black holes erupt in these brilliant jets while others do not? The answer seems to lie in the spin of the black hole itself and the complex, chaotic physics of its magnetic fields. Think of a black hole as a powerful cosmic engine. The infalling gas is its fuel, and the intense magnetic fields act like a complex set of wires and gears. If the black hole is spinning rapidly, it can twist these magnetic field lines into a tight, focused funnel, channeling a portion of the superheated material and blasting it out into the void as a jet. This is a natural particle accelerator on a scale we could never hope to build on Earth. But even the jet theory does not solve every puzzle. Some of these disruptions flare up again long after they should have faded into darkness, as if the black hole belched a second helping of stellar material. Could this mean the star was not consumed in one single bite, but is being fed upon in pieces over many years? Or is the accretion disk itself becoming unstable, buckling and reigniting in a fresh wave of violent energy? Each unusual flare is a precious data point, a fleeting laboratory for testing the limits of gravity and plasma physics under the most extreme conditions imaginable. By studying the final moments of a star, we are learning how the most powerful engines in the universe are built and powered, one catastrophic meal at a time. Even the most fundamental constants of the cosmos are now under scrutiny. We call it the Hubble constant, a number that tells us how fast the universe is expanding at this very moment. For decades, astronomers have worked to pin down its precise value, but instead of converging on a single answer, our two best methods have produced a stubborn and growing disagreement. This is the Hubble tension, a crisis that threatens to crack the very foundation of modern cosmology. One path to this number looks back to the dawn of time, to the cosmic microwave background. By meticulously mapping the subtle temperature fluctuations in this ancient light, we can work backwards using our best model of the universe to predict how fast it should be expanding today. This method is like calculating the top speed of a car by studying the skid marks it left at the very beginning of its journey. The other method looks at the universe as it is now, using cosmic lighthouses whose intrinsic brightness we know. Cepheid variable stars pulse at a rate directly tied to their true luminosity, making them perfect distance markers. By observing these stars in nearby galaxies, along with the even brighter Type 1, a supernova, astronomers can measure distances and recession velocities to calculate the expansion rate directly. This is like placing a radar gun on the car to measure its speed right now. The problem is, the two answers do not match. The radar gun shows the universe is expanding significantly faster than the ancient skid marks suggest it should be. This is not a small margin of error. It is a discrepancy that has withstood years of increasingly precise measurements. The car is not just going a little too fast, it is speeding away from our predictions. So what is wrong? Is our reading of the skid marks flawed? Perhaps our model of the early universe, which relies on the presence of dark matter and dark energy, is incomplete. Maybe there was an unknown type of particle in the primordial soup, a relic that subtly altered the physics of the Big Bang's aftermath and threw off our calculations. Or is the radar gun itself miscalibrated? Could there be something we do not understand about the Cepheid stars or the supernova, some hidden property that makes them less reliable standard candles than we believe? The most thrilling possibility is that the discrepancy is real, and our understanding of physics itself is the thing that is broken. The Hubble tension could be a sign that dark energy is not a constant, but an evolving force that has changed strength over cosmic history. It might even point toward a modification of Einstein's theory of gravity, a new set of rules that operate on the grandest scales. This single number, the Hubble constant, has become a battleground for the soul of cosmology. Its resolution will not just give us a speed limit for the universe, it will tell us whether we need to rewrite the story of everything from the first instant to the final fate. The very foundation of cosmology seemed to crack with the discovery of a cosmic ghost town. galaxies like NGC 1052DF2 drift through space as near-total anomalies, vast collections of stars that appear to contain almost no dark matter whatsoever. This finding sent shockwaves through the astronomical community as it strikes directly at the heart of our standard model of galaxy formation. That model depends entirely on dark matter's gravitational scaffolding to gather the initial gas and dust, a framework upon which luminous matter can then coalesce into stars and galaxies. A galaxy without dark matter is like a building with no skeleton, a shimmering facade that should have collapsed under the weight of its own motion long ago. The stars within NGC 1052DF2 move at speeds that perfectly match the gravitational pull of the visible mass alone. There is no extra tug, no signature of the unseen hand we have come to expect. This presents a paradox of existential proportions. If dark matter is real, how can a galaxy simply lack it? One compelling theory suggests these galaxies are not born this way, but are sculpted by violence. Perhaps NGC 1052DF2 was once a normal galaxy, rich with its share of dark matter, until it had a close encounter with a much larger neighbor. The immense gravitational field of the larger galaxy could have acted like a cosmic comb, stripping away the loosely bound dark matter halo while leaving the more densely packed stars relatively untouched. The galaxy would be left as a disembodied stellar stream, a ghost of its former self. This process, known as tidal stripping, would create the exact illusion of a dark matter-free object. Yet, other explanations are far more radical. What if our understanding of dark matter itself is flawed? The prevailing model assumes dark matter is cold and slow-moving, particles that clump together easily to form the gravitational seeds for galaxies. But if dark matter were instead warm, or even interacting with itself in complex ways we have not anticipated, it might not cluster in every single galaxy. It could be distributed in a patchwork across the cosmos, leaving some regions devoid of its presence. This would mean the rules of galaxy formation are far more varied and complex than our tidy models suggest. The existence of these strange galaxies forces a difficult choice. Either they are the mangled survivors of cosmic collisions, proving that dark matter can be torn away, or they are pristine examples that reveal a startling flaw in our core assumptions. Both possibilities are profound. One confirms the particle nature of dark matter by showing it can be separated from normal matter, while the other demands a wholesale rewrite of its fundamental properties. These seemingly empty galaxies are not just oddities, they are critical experiments written in starlight, testing the limits of our knowledge against the dark. This cosmic map of ghost galaxies and dark matter halos gives way to an even deeper emptiness, far beyond our local superclusters. In the direction of the constellation Boötes lies a region of space so profoundly barren it defies easy comprehension. This is the Boötes Void, a spherical chasm in the cosmos stretching an almost unbelievable 330 million light-years across. Within this staggering volume, you would expect to find thousands, even tens of thousands of brilliant galaxies. Instead, astronomers have catalogued only a few dozen. It is a cosmic desert on a scale that is difficult to even visualize. If our Milky Way were at the center of this void, our night sky would be almost completely black, with the nearest major galaxy a desperate, lonely voyage away. The formation of such a colossal nothingness presents a monumental puzzle. The large-scale structure of the universe is a cosmic web, a vast network of interconnected galaxy filaments separated by great dark bubbles. But the Boötes Void is not a mere bubble, it is a cavern of incomprehensible size. How could the matter of the early universe have avoided clumping here on such a grand scale? One leading theory takes us back to the universe's first moments. The seeds for all cosmic structure were planted by quantum fluctuations, tiny, random variations in energy that were stretched to astronomical proportions during a period of rapid inflation. These ripples became the blueprints for galaxies and clusters. The Boötes void, then, might be the ghost of an incredibly rare and vast underdensity, a single titanic quantum fluctuation that was almost entirely empty from the very beginning. It is a fossil from the birth of reality, a bubble of near-nothingness that has persisted for over 13 billion years. Another, more dynamic possibility involves the relentless push of dark energy. As the universe expands, the gravitational pull of matter is constantly fighting against the repulsive force of dark energy. Within an already underdense region, dark energy's influence would be more pronounced, accelerating the expansion of that local space and effectively pushing any remaining galaxies even farther apart, deepening the void over billions of years. What does this immense emptiness tell us? It reveals that the cosmic web is far more complex and extreme than we once imagined. The voids are not merely passive backgrounds, they are active players in the evolution of the cosmos, their growth influenced by the mysterious dark energy that dominates our universe. The Boötes void stands as a monument to randomness, a reminder that the initial conditions of the Big Bang could create staggering deserts alongside dense metropolitan clusters of galaxies. Is it a pristine relic of the first instant or an emptiness magnified by a phantom force? Its silent, dark expanse holds the answer, a question mark written in negative space on the grandest possible scale. A star located over 1,000 light-years away has been caught in a cosmic lie. KIC 8462852, better known as Tabby's star, behaves like no other sun we have ever observed. Its light does not merely flicker, it plunges into unpredictable, precipitous dips, sometimes losing more than 20% of its brightness for days or weeks at a time. This is not the gentle, rhythmic dimming caused by an orbiting planet. A Jupiter-sized world would block only about 1% of this star's light. The drops observed here are monstrous, chaotic, and completely aperiodic, defying any conventional explanation. The first instinct of astronomers was to look for a natural culprit closer to home. Could a vast, swirling cloud of dust and debris be orbiting the star? A massive family of comets shattered by a close encounter could potentially create a thick, irregular shroud that intermittently blocks the star's light. The problem is that such a colossal swarm would also produce a clear and distinct infrared signature, the heat glow from all that warm dust. When we looked, that infrared excess was nowhere to be found. The dust, if it exists at all, must be strangely cold or configured in a way that hides its thermal fingerprint. This dead end forced scientists to consider more exotic possibilities. What if the star itself is undergoing internal convulsions we do not understand? Perhaps it is surrounded by a warped, collapsing protoplanetary disk, or maybe it recently consumed a planet, creating a temporary shroud of debris. Yet none of these models perfectly fit the bizarre, jagged pattern of the light curve. The dimming events are too sharp, too deep, and too irregular. It was this very strangeness that opened the door to a hypothesis that sounds like it was lifted from a science fiction novel. In the search for advanced extraterrestrial intelligence, one theoretical concept is a Dyson sphere, a megastructure designed to encapsulate a star and harness nearly all of its energy output. While a complete sphere is likely impossible, a partially built swarm of energy-collecting satellites orbiting the star would produce exactly the kind of irregular, massive dimming we see. These giant orbital platforms would pass in front of the star in unpredictable sequences, casting vast geometric shadows into space. The idea is not that this is the most likely answer, but rather that it is a scientifically conceivable one that has not yet been entirely ruled out. It forces us to confront a profound question. When we are faced with a phenomenon that resists all natural explanations, at what point do we dare to consider an artificial cause? The true nature of Tabby's star remains one of the most compelling open cases in modern astronomy. It is a cosmic detective story where every clue leads to a deeper mystery, a reminder that the universe may hide engineering projects on a scale we can barely dream of. their signatures written in the fleeting shadows they cast. Even the universe's first moments left behind a chemical fingerprint we cannot fully read. In the furnace of the Big Bang, during the initial 3 minutes of everything, the primordial elements were forged. Hydrogen and helium were cooked in abundance, their predicted amounts matching almost perfectly with what we observe in the oldest stars. But there was a third element, lithium, and its numbers tell a different story. Our most precise models of Big Bang nucleosynthesis predict that a specific, small amount of lithium-7 should have been created and scattered across the cosmos. Yet when we look at the ancient population 2 stars, the venerable fossils of our galaxy, we find only about 1/3 of the lithium that our equations insist should be there. This is the cosmic lithium problem, a deficit that points to a fundamental gap in our understanding of the universe's birth. Where did all the lithium go? One possibility is that our models of the Big Bang itself are subtly incomplete. Perhaps an unknown form of radiation or a previously unconsidered particle was present in that primordial inferno, interacting with the newborn nuclei and altering the delicate nuclear reactions that produce lithium. This would mean the recipe for the universe, which we thought we had mostly correct, requires a new, exotic ingredient. The other leading suspect is the stars themselves. These ancient stars are the custodians of the universe's original chemistry, but what if they are also the destroyers of the very evidence we seek? Deep within their cores, lithium is a fragile element, easily destroyed at temperatures above 2.5 million degrees. It is possible that over billions of years, slow-burning nuclear reactions or internal mixing processes have gradually consumed the original lithium, diluting the primordial signature we are trying to measure. Think of it like an ancient parchment that has slowly faded over the millennia. The original writing is still there, but parts of it have been erased by time itself. There is even a more dramatic stellar solution. Could some of these old stars have deep, turbulent convection currents, like a giant cosmic spoon, that constantly stir their outer layers, dragging pristine lithium down into the hotter interior where it is instantly annihilated? This would make each star a tiny lithium destruction factory, systematically erasing the cosmic record. The implications stretch far beyond a single element. If the discrepancy is due to new physics in the early universe, we may have to revise our entire timeline of those first few minutes. But if the stars are to blame, then we are faced with a stunning realization. Our best cosmic laboratories for studying the infant universe are not pristine time capsules after all, but active chemical processes that have been quietly altering the evidence for billions of years. The cosmic lithium problem is a quiet but persistent alarm bell, reminding us that even our most foundational stories of creation may still be missing a crucial page. The universe's elemental puzzles are matched only by the raw, unfiltered power it can unleash. Streaking through the void are cosmic bullets, subatomic particles carrying so much energy that their origin seems almost impossible. These are ultra-high energy cosmic rays, and they arrive with a force millions of times greater than anything our most powerful particle accelerator, the Large Hadron Collider, can produce. A single one of these particles, smaller than an atom, can hit our atmosphere with the kinetic energy of a professionally served tennis ball, all concentrated into a microscopic point. They are the fastest, most energetic things we know of in the universe, and we have almost no idea what is firing them at us. The central mystery is not their existence, but their source. Charged particles like protons are deflected by the magnetic fields that weave through interstellar and intergalactic space. It is as if these cosmic rays are trying to navigate a hall of mirrors while blindfolded, their paths twisted and scrambled so thoroughly by the time they reach us that tracing them back to their point of origin is a monumental challenge. They are cosmic orphans arriving with a bang but no return address. So what cosmic engine could possibly accelerate a single particle to such ludicrous speeds? The suspects are as extreme as the crime itself. One leading candidate is the active galactic nucleus, the supermassive black hole at the heart of a galaxy, greedily feeding on surrounding matter. The intense magnetic fields and swirling accretion disk around such a monster could act as a natural particle accelerator of unimaginable scale, capable of firing protons across the universe like a cosmic railgun. Another possibility involves the cataclysmic deaths of massive stars. The shock waves from a supernova explosion can, in theory, accelerate particles to tremendous energies, but whether they can reach the very highest levels we observe remains an open question. When these conventional explanations fall short, physicists turn to the exotic. Could these particles be the dying breath of super-heavy dark matter? This theory suggests the early universe was filled with a population of incredibly massive, as yet undiscovered particles. As these relics of creation slowly decay, they could release their immense mass energy, spawning the ultra-high energy cosmic rays we detect. It is a ghostly process where the invisible dark matter that shapes the cosmos finally reveals a faint, explosive signature in its death throes. Another speculative idea points to defects in the very fabric of space-time. Cosmic strings, hypothetical one-dimensional cracks in the universe, or other topological defects from the Big Bang, could snap and release titanic bursts of energy as they evolve, creating the perfect conditions to launch these particles on their interstellar journeys. Each detection is a message from a cosmic battlefield, a fragment of a story about the most violent processes in existence. Are they the exhaust from a supermassive black hole, the final whisper of a dark matter giant, or the snap of a cosmic flaw? For now, these unidentified high-energy particles remain both a testament to the universe's power and a quiet admission of how much we have yet to learn about its most fundamental forces. Far above the cloud tops of Saturn, a shape holds its form against the chaos. At the planet's north pole, a hexagon of clouds wider than 2 Earths has maintained its perfect 6-sided geometry for decades. This is not a fleeting atmospheric whim, but a permanent fixture, a colossal piece of celestial geometry etched into the sky of a gas giant. It is a feature without parallel in our solar system, a puzzle of fluid dynamics on a scale we can barely comprehend. How can a storm, a system of churning winds and turbulent gas, lock itself into such a rigid mathematical form? The answer lies in the behavior of the atmosphere itself. Scientists believe the hexagon is a manifestation of a meandering jet stream, a river of air flowing at high speed around the planet's pole. Here on Earth, our jet streams snake across the globe in great, wavy undulations. On Saturn, something different occurs. Laboratory experiments with spinning fluids have shown that under the right conditions, a stable, polygonal pattern can emerge around a central vortex. The speed of the rotation and the properties of the fluid can dictate the number of sides, from a triangle to an octagon. Saturn's specific conditions of wind shear and planetary rotation seem to favor a perfect hexagon. It is a standing wave frozen in place by the planet's furious spin. Yet the laboratory models, while compelling, cannot fully explain the hexagon's stunning longevity and razor-sharp definition. Why does it have exactly 6 sides, and why have those sides remained so stable, resisting the dissipating forces that should have blurred its edges over time? Some theories suggest the hexagon is a towering structure, a wall of clouds that extends hundreds of kilometers deep into the atmosphere, its roots anchored in processes far below the visible cloud decks. This depth could provide the stability needed to maintain the pattern against the buffeting winds. Others point to the possibility of multiple, smaller vortices whirling around the central pole, their collective dance shepherding the main jet stream into its hexagonal corral. The precision of this shape challenges our intuition about weather, reminding us that the laws of physics can produce order from chaos in the most unexpected ways. Is the Saturn hexagon a beautiful, natural resonance, a harmonic of the planet's own spin and atmospheric composition? Or does its persistence hint at deeper, hidden layers of circulation we have yet to discover, a secret engine of stability within the gas giant's heart? This six-sided wonder is more than a curiosity. It is a laboratory in the sky, testing our understanding of how fluids behave when a world itself is the spinning bowl. After the primordial fireball of the Big Bang faded, the universe entered a profound and quiet darkness. For hundreds of millions of years, a thick fog of neutral hydrogen gas filled all of space, a featureless sea where light could not travel far. This was the cosmic dark ages. Then, something extraordinary happened. The first stars and galaxies ignited, and their brilliant, harsh light began to burn away the fog, transforming the entire cosmos in an event we call the reionization era. This period marks the universe's final major transition, when it became the transparent, star-filled expanse we see today. Yet, how this happened remains one of our greatest cosmic puzzles. What were these first objects like, and how did they manage to ionize the entire universe? The first stars were not like our sun. They are known as population 3 stars, and they were behemoths, giants hundreds of times more massive than our own star. Forged from the pristine hydrogen and helium of the early universe, with no heavy elements to cool them, they burned at ferocious temperatures and lived fast, violent lives. Their intense ultraviolet radiation acted like a cosmic blowtorch, stripping electrons from the surrounding hydrogen atoms and turning them from a neutral fog into a transparent, ionized plasma. But here lies the core of the mystery. Could these first massive stars alone have produced enough radiation to reionize the entire cosmos, or did something else contribute? The timeline is incredibly tight. Observations suggest reionization was largely complete by the time the universe was about 1 billion years old. That means these first luminous objects had to form, live, die, and flood the universe with enough energy to clear the fog in a relatively short cosmic span. It is like needing to evaporate an entire ocean with a finite number of blowtorches, and we are not sure we have found enough of them. This is where the newest generation of space telescopes enters the story. The James Webb Space Telescope is our most powerful time machine, designed to peer back into this very epoch. Its mission is to hunt for the faint, redshifted glimmers of those first galaxies and stars. Are they ultra-bright with frenetic rates of star formation, or are they more numerous and smaller than we predicted? Each new galaxy it finds is a data point in this grand cosmic equation. Could early supermassive black holes, voraciously feeding and pouring out radiation, have provided a crucial assist, or did the deaths of those first massive stars in spectacular supernova play a vital role, their shockwaves clearing vast bubbles of transparency in the hydrogen fog? The reionization era was not a gentle sunrise, but a chaotic and fragmented dawn. It likely happened in patches, with ionized bubbles growing around clusters of early stars and galaxies until they finally overlapped and filled the entire universe with light. We are only now beginning to map the outlines of this epic transformation, an event that lit the way for every star and galaxy that would follow. The answers will tell us how our universe emerged from its dark, formless infancy to become the brilliant, structured cosmos we call home. Some stellar explosions refuse to follow the rules. Between the brilliant death throes of supernova and the smaller flashes of classical nova lies a strange and rare class of cosmic outburst, the luminous red nova. These events are brilliant enough to be seen across galaxies, yet they are not the final demise of a star. They are something else entirely, a violent and mysterious transformation. The most famous of these is the star V838 Monocerotes. In 2002, it erupted without warning, becoming 600,000 times brighter than our sun in a matter of days. But instead of fading away or collapsing, it did something astonishing. It began to swell, expanding at a phenomenal rate to become one of the largest stars ever recorded. A titanic sphere of gas so vast it would have engulfed the orbit of Jupiter had it been in our own solar system. This was not a simple explosion, it was a stellar metamorphosis. So what could cause a star to flare with such incredible violence and then bloat to an unimaginable size? The leading theory points to a cosmic collision, a stellar merger. Imagine two stars long bound in a gravitational dance, finally spiraling into each other. Their violent union would unleash a cataclysmic outburst of energy and light, followed by the newly merged star puffing up into a single, gigantic, and unstable red supergiant. This would explain the sudden brightening and the subsequent rapid expansion. Another possibility is a star consuming its own planetary system. A sun-like star ingesting a gas giant planet like Jupiter could trigger a massive thermonuclear eruption on its surface. The sudden infusion of hydrogen-rich fuel could ignite a runaway fusion process, causing the star to flare brilliantly and its outer layers to balloon outward. Yet another idea involves a novel kind of surface explosion, a helium flash on a massive scale, where a shell of helium around the star's core ignites in a sudden, brilliant fusion fire. Each of these theories paints a picture of stellar chaos and rebirth. The case of V838 Monocerotes is so important because we witnessed the aftermath in unprecedented detail. The Hubble Space Telescope captured the progression of its light echo, a shell of illuminated interstellar dust expanding away from the star like a ripple in a pond. This echo provided a three-dimensional map of the event, confirming the immense scale of the outburst. Was it a fatal embrace between two stars, the final course of a planetary feast, or a new type of stellar physics in action? The luminous red nova remind us that stars are dynamic, sometimes violent entities, capable of changes so profound they challenge our very definitions of stellar life and death. Our universe is built upon two separate sets of rules that cannot both be true. The world of the very large is governed by the smooth, geometric fabric of spacetime, as described by Einstein's theory of general relativity. It is a continuous stage where gravity is the curvature created by mass and energy. Yet, the world of the very small, the realm of atoms and particles, operates under the chaotic, probabilistic rules of quantum mechanics. Here, everything is granular, jumping between discrete energy levels. These two theories are the most successful and accurate descriptions of reality we have ever devised, but they are fundamentally, violently incompatible. When we try to apply the equations of gravity to the quantum scale, or inject quantum rules into the heart of a black hole, the mathematics breaks down into nonsense, producing infinities where there should be physical answers. This is not a minor technical issue, it is a chasm at the very foundation of physics, and bridging it is perhaps the greatest intellectual challenge of our time. So what is the true nature of spacetime? Is it a smooth continuum, as Einstein believed, or is it woven from something more fundamental? The quest for a theory of quantum gravity seeks to answer this by finding the hypothetical atoms of space and time themselves. One leading candidate is loop quantum gravity. This approach takes the geometry of spacetime quite literally, proposing that space is not a background void, but a dynamic fabric woven from an incredibly dense network of finite loops. These loops, or threads of gravitational field, form a spin network, a structure that evolves over time. Think of it as a cosmic tapestry, where each individual thread is a billion times smaller than an atomic nucleus. The fabric of reality is not smooth, but a mosaic of these tiny, quantized elements. In this view, the continuity we experience is an illusion, much like a movie appears fluid despite being made of individual frames. Another, even more ambitious framework is string theory. It proposes that the fundamental constituents of the universe are not zero-dimensional points, but incredibly tiny, vibrating one-dimensional strings. The different vibrational patterns of these strings manifest as different particles, one vibration for an electron, another for a quark, and a specific pattern for the graviton, the hypothetical quantum carrier of gravity. This elegantly unifies all forces and matter under a single concept. However, the theory requires something extraordinary, that the universe has extra spatial dimensions, perhaps 6 or 7 of them, all curled up into a size so infinitesimally small that we never perceive them. It is as if we are ants crawling along a vast, thin garden hose, completely unaware that the hose itself has a circular dimension. The challenge is that these ideas are currently almost impossible to test experimentally. The energy levels required to probe such tiny scales are far beyond anything we can create. So we are left with a cosmic standoff, two brilliant but unproven visions of reality. One pictures space as a granular structure, the other as a symphony of vibrating strings in a higher dimensional arena. The resolution to this conflict will not just tell us how gravity works on a quantum level, it will reveal what reality is truly made of at its most fundamental core. Is the universe a cosmic computation running on a network of space-time atoms, or is it a multidimensional vibration? The answer waits in the quiet space between our two best descriptions of everything. These cosmic phantoms drift through the void, vast and yet almost invisible. Ultra-diffuse galaxies are the ghosts of the cosmos, spanning the same immense volume as our own Milky Way, but containing only a tiny fraction of its stars. A galaxy like Dragonfly 44 is a perfect example, a colossal structure of staggering size that shines with just 1% of the stellar light we would expect. It is a city built on a planetary scale, with its streetlights spaced so far apart that the entire metropolis appears dark and abandoned. The central mystery is not just their faintness, but their very existence. According to our established laws of gravity, a structure this large and this sparse should not hold itself together. The meager gravitational pull from its few stars should be entirely insufficient to prevent the galaxy from simply dissolving back into the void. So what unseen hand is keeping these ghost cities intact? One compelling theory suggests these are failed galaxies. In the early universe, a vast cloud of dark matter began to gather gas, poised to become a brilliant new island of stars. But then something went wrong. Perhaps a nearby quasar or a fierce stellar wind from a neighboring galaxy blasted away its star-forming gas before it could properly collapse. Starved of its primary fuel, the galaxy was stillborn, left as a dark matter halo with only a sprinkling of ancient stars, a cosmic skeleton that never gained flesh. Another, more violent explanation points to internal rebellion. Imagine a young, compact galaxy where the first generations of stars are born. These massive stars live fast and die young, exploding as supernova in a relentless, coordinated onslaught. This series of stellar detonations could have acted like a cosmic pump, injecting so much energy into the galaxy's gas that it puffed the entire structure up from the inside out, scattering its stars into a wide, diffuse cloud from which it could never recover. The galaxy would be a victim of its own tumultuous birth, stretched thin by its internal fury. This leads to the most critical question of all. If these galaxies are held together by immense halos of dark matter, as Dragonfly 44 appears to be, then they become perfect natural laboratories. With so few stars to create a blinding glare, astronomers can study the distribution and behavior of dark matter with unprecedented clarity, mapping the ghost by the shape of its haunt. Yet, the discovery of some ultra-diffuse galaxies that seem to have very little dark matter at all deepens the puzzle, suggesting that the pathways to forming these spectral structures are more diverse than we ever imagined. Are they the failed dreams of the cosmos, the survivors of internal explosions, or something else entirely? Their faint light carries the story of a universe where even failure can create something of breathtaking scale and mystery. Our cosmic yardstick has a wobble we cannot explain. Cepheid variable stars are the foundation of our cosmic distance ladder, the crucial stepping stones that allow us to measure the vast expanses between galaxies. These aging, giant stars pulse with a regular rhythm, brightening and dimming in a cycle directly tied to their true intrinsic brightness. By observing the period of this pulse, we know exactly how luminous the star should be, and by comparing that to how dim it appears from Earth, we can calculate its distance with remarkable precision. Or at least that is how it is supposed to work. Astronomers are now finding cepheids that break this simple, elegant rule. Some of these stellar mileposts pulsate in 2 or even 3 different modes at the same time, like a drum producing several different beats from a single skin. Others exhibit strange, unexpected variations in their brightness cycles, subtle irregularities that should not exist. This is more than a minor curiosity. It is a direct threat to the accuracy of our entire cosmic map. The Hubble constant, the very rate of the universe's expansion, is measured using this ladder. If the rungs themselves are unstable, our most fundamental measurement of the cosmos could be wrong. The frantic search for an answer leads us deep into the chaotic hearts of these dying stars. A cepheid is a stellar engine in its final, unstable chapters, its outer layers rhythmically expanding and contracting. This pulsation is a delicate balance between 2 opposing forces, the outward pressure of radiation and the inward crush of gravity. But what if the internal structure of these stars is more complex than our models assume? Perhaps powerful magnetic fields twisting deep within the star are altering the pulsations. Or maybe the chemical composition is not uniform, with layers of different elements churning and interfering with the star's natural rhythm. Think of it like trying to predict the exact pitch of a bell. If the bell is made of a single, pure metal, its tone is clear and predictable. But if the bell is an alloy with pockets of different densities and impurities, its chime becomes complex and slightly off-key. These anomalous cepheids might be the cosmic equivalent of those impure bells, their complex interiors creating a symphony of pulsations that our simple models cannot yet decode. Solving this mystery is a painstaking process of stellar forensics. Astronomers are using advanced satellites to monitor the faintest flickers of these stars, gathering data on their light, their temperatures, and their velocities. At the same time, astrophysicists are running immense computer simulations, attempting to build a digital star that can finally replicate this bizarre multi-mode behavior. They are trying to create a virtual cepheid so realistic that it spontaneously exhibits the same strange pulses we see in the real thing. The implications are staggering. If we cannot trust the cepheids, the entire cosmic distance ladder may need to be recalibrated, forcing us to revise the size, age, and expansion rate of the universe itself. Is the Hubble tension, the disagreement over how fast the cosmos is flying apart, partly a result of our own flawed rulers? The quiet, rhythmic beating of these distant suns holds the key to a measurement that defines our place in the cosmos, a pulse we are only now realizing we might have misread all along. That rhythmic pulse of the cepheid stars measures a cosmic race whose finish line we cannot yet see. The ultimate destiny of everything, from the largest galaxy to the smallest atom, hinges on the final, silent battle between the relentless expansion driven by dark energy and the persistent inward pull of gravity. The fate of the universe is not written in stone, but in the unknown nature of that phantom force. One possible end is a quiet, cold, and lonely demise known as the Big Freeze. In this scenario, dark energy maintains its current, steady push. The expansion of the cosmos continues forever, accelerating galaxies away from one another into an ever-deepening isolation. Over trillions of years, stars will exhaust their nuclear fuel, one by one, winking out into black dwarfs or exploding, scattering their heavy elements into the void. Galaxies will fade from view, their light stretched into undetectable wavelengths. The universe will slowly cool toward absolute zero, a state of maximum entropy where no energy can be harnessed, no new stars can form, and all activity grinds to a permanent halt. It is a heat death, a cosmic graveyard of infinite space and eternal, frozen silence. A far more violent alternative is the Big Rip. This terrifying outcome depends on dark energy not being constant but growing stronger over time. If its repulsive force intensifies, it would eventually overcome every binding force in the universe. First, galaxy clusters would be torn apart, then individual galaxies. As the force grows, stars would be ripped from their galactic homes. In the final, cataclysmic moments, the escalating expansion would tear apart planets, then stars themselves. Ultimately, even atoms, nuclei, and the very fabric of space-time would be shredded. The universe would end not with a whimper, but with a final, instantaneous scream, as every single structure is dissolved into its most fundamental, disconnected particles. There is, however, a third cyclical possibility, the Big Crunch. This scenario requires that dark energy weakens or reverses, allowing gravity to finally win the cosmic tug-of-war. The expansion of the universe would slow, halt, and then reverse. All of creation would begin to rush back together, galaxies merging in a spectacular, fiery collapse. The temperature of the cosmos would soar as everything is compressed into an inferno of unimaginable density, potentially culminating in a singularity mirroring the Big Bang itself. This singularity might then rebound, sparking a new Big Bang and birthing a new universe from the ashes of the old, in an endless, cyclic dance of creation and destruction. Our entire cosmic history could be just one chapter in an infinite loop. Which of these destinies awaits us? The answer lies in the precise equation of state of dark energy, a value we are still struggling to measure. Is its push constant, or is it dynamically evolving? Our observations of the universe's accelerating expansion point toward a big freeze, but the data is not yet conclusive. The true nature of this dominant force remains the final and greatest mystery on our list. It is the question that gives meaning to all the others. For every enigma we have explored, from dark matter's grip to the birth of the first stars, is part of a story whose final page has not yet been written. The ultimate fate of reality itself is the final, silent question hanging in the vast, dark expanse. 25 profound mysteries stand as a testament to our endless curiosity. We have journeyed from the ghostly pull of dark matter holding galaxies together to the phantom push of dark energy tearing them apart. We have been drawn toward the unseen Great Attractor and confronted by the deafening silence of the Fermi-paradox. The universe has spoken in cryptic bursts, from the singular wow signal to the repeating fury of fast radio bursts. Our own probes whispered of an anomaly in the dark, while the frozen edge of our solar system presented a cliff with no easy explanation. A strange visitor, Oumuamua, tumbled through, defying categorization, and the oldest light in the cosmos revealed a potential axis of evil that could unseat our most fundamental principles. We grappled with information falling into black holes and stars being shredded by them. We measured an expanding universe that cannot agree on its own speed, and we found galaxies that should not exist without dark matter, and others that seem to have none at all. We explored a void so vast it defies reason, a star that dims in ways we cannot explain, and a primordial lithium deficit that hints at physics beyond our current grasp. We witnessed cosmic rays of impossible energy, a perfect hexagon spinning on a gas giant, and the epic dawn when the first stars burned away the universal fog. We saw stars erupt and transform in luminous red nova, and strained to unify the laws of the quantum world with the force of gravity. We catalogued the ghostly vastness of ultra-diffuse galaxies and questioned the very stellar mileposts we use to map the cosmos, all while contemplating the final fate of everything in a silent battle between expansion and gravity. Each one of these enigmas reveals that the cosmic void is not empty at all. It is filled with questions, each a beacon calling us to look deeper, think harder, and venture further. The universe is a story still being written, and we have only just begun to read the first few lines. We would love to hear which of these cosmic mysteries captures your imagination the most. Was it the potential for alien technology in a strange interstellar object, or the terrifying possibility of a final big rip? Let us know your thoughts in the comments below, and if you are ready for more journeys into the unknown, be sure to subscribe. Our next adventure into the deepest wonders of the cosmos is already